Yeah, no problem. So, no answer, I guess everyone, I guess it's good, Well, okay. So, I'm going to start. So, hello everyone. My name is Axel Marmoret. I'm a Ph.D. student at IRISA in France. And I'm here to present you my PhD work I've entitled Unsupervised Barwise Compression for Pattern Uncovering and Structural Segmentation. So just in the first introduction, so I'm doing my PhD in Rennes, so it's in the west side of France. So here it's a little dot, and this PhD co-supervised by Frédéric Bimbaud and Jeremy Cohen, which are both researchers on signal processing side. And I'm also working with Nancy Bertin and Simon Lefebvre, but which are not in supervision per se. In very short, my PhD subject is about structural segmentation of music. So starting from an audio signal, the objective is to obtain some kind of global organization of the song. So here, a very simple example. I'm going to get into more details after. Okay, so to give you an overview of what this presentation will be about, let's start with the title. So this is entitled Unsupervised Music Compression for Pattern Uncovering and Structural Segmentation. So first, music will be treated in form of audio signals. As any other signal, any signal in music, it will be transferred into some kind of feature representation. So here we will mostly focus on short time Fourier transform, Mel spectrogram, and chromogram. The first thing is that this music will be treated barwise. So we will do barwise processing. We'll split the spectrogram in barwise elements. This will not be the heart of this presentation. This work is not about how to treat music barwise. We just use a toolbox, here the Madman toolbox, and don't look at how to do it. So basically, the work today is going to focus on the three last blocks: the unsupervised compression part, and how to do this, how to use this compression for structural segmentation of music and pattern uncovering. So, guideline here. I will first talk about structural segmentation. I will then present three different compression methods called non-negative decomposition, Barwise compression schemes, and auto-encoding MDT. These are three different compression schemes, three different methods of compression, and these compression are then used to infer structures, to do structural segmentation or to uncover patterns. So this is what this talk would be about today. First, let me talk about structural segmentation. As I already kind of presented, the idea of structural segmentation is to retrieve a global organization of the structure of the song. So here on an example, I'm taking a song which is organized in a verse, then a chorus, another verse, a solo, and then a final chorus. The idea of structural segmentation would be to retrieve this kind of structures, and structure can be on different level. The level I'm talking about today is the highest one, the one corresponding to the sectional level, to the level I've entitled chorus versus the levels the musician intended at the higher scale. And starting from the lowest scale available, which is the bar scale, as I've stated in the introduction, the goal would be to go up from the bar scale to the sectional scale. Precision, I'm not talking about how to label segments. I'm just focusing here on boundary retrieval, which means finding the different boundaries between different segments. So why should we do structural segmentation? Not to be exhaustive, but we could think of structural segmentation for structural analysis per se. So for instance, to do some musicology analysis or to summarize the content of a song. We could also use structure for as a mid-level feature, for instance, in such tasks as genre, music recognition, recommendation, or cover detection, or many others, I guess. But what I will focus today is we will use structure as a quantitative evaluation, which means that I will evaluate the relevance of the compression model I will present in the structural segmentation task. It's a way to quantitatively evaluate the model. So, how to find structure now? Structure will be studied here as a compression scheme. The general models to find structure are generally divided between what is called homogeneity, the idea of having a segment which is homogeneous in itself, between novelty, which is kind of the opposite, finding novelty between two different sections, repetition, if some piece, some patterns is repeated itself a lot, it should be a segment, or regularity. For instance, every 4 bars you have a frontier or a boundary or this kind of regularity in the music. And we encompass the first 3 under the broader redundancy term. And this leads to the compression scheme. I won't go into much more details here, but we also account for regularity with constraints in my work. Now, as I was saying, in addition to seeing music, we will segment the music in different bars. So we take the Barwise point of view to study structure based on 2 hypotheses. The first one is that patterns in music, or at least in the music we're studying, tends to develop at the bar scale. So, and the second hypothesis will be that boundaries generally fall on downbeats. This is 2 hypotheses that kind of could lead us to study music barwise. And concretely, what we will do is that starting from some spectrogram in any representation, we will evaluate the bars and cut these spectrograms at the downbeats. So we have a collection of Barwise spectrograms. This is what I call Barwise processing here. Detail, but as bars can be of different size, we fix the number of frames in each bar. It's an hyperparameter. And now, starting from this Barwise scheme, we will evaluate the structure in what we call an autosimilarity matrix. So basically, the idea of an autosimilarity matrix is to compute similarity between 2 bars of the song, and the matrix is presenting these similarities between all pairs of bars in the song. Yeah, it's kind of maybe a little bit small, but the idea is to, like, for any index in the matrix, we take 2 bars on the original song, and we compute a similarity which is just a dot product between these 2 bars, which is normalized. This is called the cosine similarity, and it gives us a measure of how similar these 2 bars are. For all pairs, this gives us a matrix. And we will focus here on segmenting this autosimilarity. We see that some kind of block patterns are emerging from this matrix, and this is what we will try to find here. The gray lines represent the annotation of this song. And this structure from this autosimilarity matrix will be found using an algorithm we have called the convolutive block matching algorithm. So the general idea is that there is some kind of block structure on the diagonal. If I go back to the chromogram of stay on the mic. But if I go back to the autosimilarity of the chromogram of come together, we can see some kind of a block structure on the diagonal here. And the algorithm is intended to find this block structure here and to frame the different blocks. This is done via dynamic programming. We can go into details later, but just here is to give you the idea of how we retrieve structure and the boundaries from an autosimilarity matrix. And yeah, the code is open source if you want to go take a look. And this algorithm in practice already gives interesting results that we would like to a bit. I've presented here 3 on the left part. Oh yeah, first, what are the matrices? The matrices here are based on what we call the iterate rate. Starting from boundaries we have estimated and boundaries we have annotated. The idea would be to look how close the estimation are from the annotation. A boundary will be considered valid if it falls within a tolerance from the annotation, and will be considered invalid otherwise. We use 2 different tolerances, which are standards in structural segmentation, which are 0.5 seconds, so it's kind of the closest range, and 3 seconds. So here I have with invalid and valid boundaries, I have true positives, false positive, and false negative. So I can compute precision, recall, and F measure. And this is why I'm displaying here. I'm displaying the F measure for 0.5 seconds tolerance and 3 seconds tolerance. Maybe with the light it's not clear here, but. And finally, I will present results on the RWC popular dataset, which is a benchmark of popular songs, generally, which is a lot used in structural segmentation. And yeah, the different algorithms I'm presenting here are 3 of the unsupervised state-of-the-art algorithm, novelty kernel from Fruit, convex NMF from Nieto, and spectral clustering from McPhee and Al. And this unsupervised algorithm here are obtaining similar results from what we have with our convolutive block matching algorithm. Here on the right, I have displayed the nowadays state-of-the-art method for segmenting the RWC popular dataset, which is a convolutional neural network. And it still is way better than our technique. But my goal today will be to show that with compressed representation, we can increase these scores which were computed on the feature similarity matrix directly. So to be clear, what I'm showing you here is segmentation results when we apply our algorithm on the auto-similarity matrix computed from the raw feature representation. So chromogram, log-mail spectrogram, and any other representation, but here you see chromogram and log-mail spectrogram. And we'll kind of see how compression can improve these results and compare with this unsupervised and supervised algorithm. Now let's introduce the first model, which is called non-negative Tucker decomposition. The idea of non-negative Tucker decomposition is a tensor decomposition method. What is a tensor first? A tensor is kind of a generalization of matrices. So if we see a matrix as a rectangle, tensors can be high-dimensional array with more than 2 dimensions. In particular, here we will study third-order tensors, which are parallelepiped, kind of a cube or some kind of parallelepiped. And this is a third-order tensor. Here we will obtain this tensor called TFB tensor for time frequency bar when we split the original spectrogram in different bars. So we have a collection of Barwise spectrogram, as I told you earlier. And we create the third dimension with the different bars. So to be clear here, I have the frequential dimension, for instance, the mel, the chroma, etc. Here I have the time at the bar scale inside of a bar, and on the third dimension I have all the different bars in the song. It's a collection of Barwise spectrograms. And this is a tensor we study in the non-negative Tucker decomposition model. But first, to explain what is non-negative Tucker decomposition, I'd like to go back on more studied in the music information retrieval domain, which is the non-negative matrix factorization. Here I'm showing the non-negative matrix factorization example on a task which is in music transcription. The idea is just starting from the spectrogram of a song. Here it's Au clair de la lune, a famous French song. In this song, we're expecting to find 3 different notes, G, A, and B. I think it's G, A, and B. And starting from this spectrogram, we will factorize the content of the spectrogram in 2 matrices, W and H. And we expect the first matrix W to have frequential templates corresponding to different notes, so G, A, and B here. And in the matrix H, we have the corresponding activations of these different nodes. So in conventional matrix product, we have the first column of W, which is a note, and its corresponding activation is the first line of H. And the different columns of W are corresponding to the activation of the corresponding line in H. So we have frequential templates and their activation in time. So it's just X equals WH, or is approximated. I would like to have a more expressive model, and this is what I'm showing you here by adding a new matrix J. Matrix J is a mixed matrix which will take templates of W and templates in H and line in H, and with this red dot here, square, it will mix the different columns in W with the different lines in H. W is still a frequential template, all still frequential templates, but instead of having one line of H for each line of W, we now have different lines of H which could be composed with different lines of W. And in general, I can have a mixed matrix which will mix different columns in W with different columns in H. The idea here is to not to have the corresponding activation of each column, but to create some kind of rhythmic templates which could be activated with the frequential templates we found. So if I'm printing here a simple example of drum patterns, I'm going to play it again. So the idea is just you have the hi-hat on every beat, every quarter note, snare on the 2 and 4, and a kick on the 1, the 3, and a syncopated 3. So the idea of the model I'm presenting here is to have frequential templates in the matrix W. So here's the hi-hat, the snare, and the kick. And it's the score here, but you can imagine frequential templates instead, corresponding to hi-hat, snare, and kick. And in H, we'll have rhythmic templates at the scale of the bar, and we will reproduce the score with a combination of some of the templates in W and some of the templates in H. So here to have hi-hats on every the hi-hat on the every quarter note, every beat, every fourth beat, every beat here. We can compose the hi-hat frequential template with the second and the third line in H, and this will correspond to having an hi-hat on every quarter note. Well, here the rhythmic, okay. I can do the same with the snare and compose the frequential template of the snare with this line in H, which will correspond to activation on the second and the fourth beat. I can do the same with the kick. Here, by composing it with the third line in H, every time this is defined by this matrix J. And by composing the kick with the third line in H, we are saying the kick must happen on the first and the third beat. And finally, to have the syncopated last kick, we'll use the last line in H. So basically, we're representing a musical pattern at the scale of a bar by factorizing the frequential content in a matrix and a rhythmical content in a matrix. You can see that as dictionaries of notes and dictionaries of rhythmic templates, and you're just mixing them to obtain some new kind of templates from just these elements of these dictionaries. So what I call a pattern, and what I will call pattern in the rest of the presentation, is this kind of object. A dictionary of frequential template, a dictionary of rhythmic template, and a mixed matrix which define mix between both to obtain some kind of spectrogram, some kind of, well, it depends on the representation, of course, but some kind of musical pattern. And here it will be at the bar scale. So H is always time at the bar scale. Now I have defined one mixed matrix J, but I can define several mixed matrix J with the same dictionaries. Here the idea will be to, sorry, going a bit fast. The idea would be to define several mixed matrices, and each of these mixed matrices will define a musical pattern. And I can have different musical patterns by composing different frequential and different rhythmic templates. I will add to this model where I have here 4 mixed matrices, a new vector, which is called Q, which indicates which of the different mixed matrix, how important is this mixed matrix. And this vector Q basically make a convex combination of these different patterns. This is what is made with this mathematical equation in the bottom. The idea is that every element in Q is linking to a pattern in the product WJH, and as Q will be an integer or composed of integers or real coefficients, it will be a combination of different patterns. So I will combine different patterns, and as every pattern is a spectrogram, I will in the end have the sum of different spectrograms, and hence. So this is the sense of this Q matrix here. And now with this, yeah, it's kind of hard to get the sense at the first sight, but the idea is to factorize every content and then express the musical information in X with different patterns we could have in mind, have in stock. And finally, each of these spectrogram as a bar scale, we could define several Q matrices for several indication of patterns to have several bars. The idea here is that I have here the 5 bars, which are defining 5, I have a song with 5 bars, and each of these bars will be represented in the Q matrix as a combination of different patterns. So it's the same kind of patterns for the song, and each bar is defined as patterns. And this is the sense of non-negative Tucker decomposition. The idea is to represent a tensor X. This is the TFB tensor I've presented at the first at the start, and to represent it with a matrix W, which is frequential templates, matrix H, which will be rhythmic templates, and a tensor, core tensor J, which will be several patterns and several mixed matrices between these templates to form patterns. And then a matrix Q, which indicates which patterns are important in which bar. It's called non-negative because all factors are non-negative. So in practice, we've run this model on Chromograms. So here is the song "Come Together" by the Beatles, and it's not very visual, but the idea here is to have the different bars in the song expressed in chroma. So each one of these slices is a Barwise chromogram of the song, or spectrogram, and we will decompose this song with the matrix W here. We fixed it to the identity because at the chromogram scale, which is just a 12 semitones Western scale, we considered it was not really important to have templates which are mixing different notes. So we just fix it to the identity to have one column representing one and only one semitone. Here you have the matrix H, which corresponds to the rhythmic templates. And we could see here on the first line some kind of activation on every 8th note, or it's kind of look like activation on every 8th note. And the other lines, the other templates look like activation at some place of the bar. So we count to every place in the bar. Here in the matrix J, we have different slices, so it's not very easy to interpret and to see what is in there. The idea is just to imagine each matrix and the combination of each matrix and see that it's a mix between some columns of W and some columns of H, and it corresponds to patterns. And finally, the matrix Q, which will be what interests us for the structural segmentation part, is an expression of each bar. I will display it here. It's an expression of each bar. So here, each column is a different bar on the song, with the different patterns defined with W, J, and H. So again, each of the slices of J here multiplied by W and H is defining a chromogram, which is a pattern, and Q is expressing each bar with these different patterns. And what is particularly interesting in this example is that most bars appear as sparse combination of musical patterns. So we have some kind of sparse feature representation for each bar in the song. So now using this Q matrix, I will compute the autosimilarity matrix. So for each bar, I'm taking the corresponding column in Q and I'm making the dot product with the all other bar in the song, which leads to similarity product of each pair of bars in this Q matrix. And this gives us this autosimilarity matrix, which when I'm comparing it to the autosimilarity matrix of the chromogram itself I was showing at first, we can see that the Q, autosimilarity of the Q matrix, is exhibiting some kind of block structure on the diagonal. This is actually why we designed these algorithms this way, to account for this block structure on the diagonal. And especially this matrix seems more sparse, it seems sparser than the autosimilarity of the chromogram. So it could disambiguate the difference between different segments. Or at least that's what we hope so. And to confirm that, we saw some segmentation results on this NTD representation. And we observe that computing the algorithm on the raw chromogram obtain way significantly worse results than computing segmentation on the NTD representation, or on the Q matrix, as I've just showed you before. So using the non-negative circle decomposition and this pattern feature, we obtain much better segmentation score than on the raw chromogram feature. So here on the same tolerances and F measure I've shown you before, it's true at 0.5 and 3 seconds. It's better than all the other unsupervised methods, but it's still way below, or still below, the convolutional neural network, which was presented, which is still state of the art of this task. So this is non-negative circle decomposition in segmentation. I've insisted a lot on the fact that this decomposition finds patterns, but I haven't shown you any patterns. I've just shown you theoretical ideas and theoretical property expectations, but I haven't shown you what are the real results on patterns. So this is what I will try to do here. So recall that a pattern is one slice of J, so one mixed matrix between the collection of mixed matrices. This is what is expressed here with this crazy triple column formula, multiplied by frequential coefficients in W and frequential and rhythmic coefficients in H. To do that, we have run the experiments on short time Fourier transform, because short time Fourier transform can be recasted into audio signals with the Griffin-Lin algorithm. It's not a perfect algorithm. This is what I will show you here, because when I take the audio signal of come together, I find the short time Fourier transform and keep only the modulus, and then I find an audio signal with this Griffin-Lin algorithm. We already obtained some kind of blurry signal. So again, we will hear some artifacts which have been added from the original signal by this algorithm. Now I will do the same thing, but with the NTD output. So I still got the STFT of the song, and from this STFT, I will run NTD on Barwise spectrograms, keep only one musical pattern, the one which is most important in the introduction, and turn it into audio signal with the Griffin-Lin algorithm. Something I haven't said yet about NTD is that it's an optimization problem, so it depends on the cost function. Traditionally, so it's here, this is what I've shown here with the tensor X, which is the input, and the NTD here, which is this tensor product. And basically, the most standard, I guess, optimization function would be the Euclidean norm, and this is what we've run for the NTD actually. But when we listen to patterns obtained with the Euclidean norm, it's kind of disappointing. It looks like that. Sorry. So it's mostly like some kind of you hear some rhythmic, I'm going to find the word. Sorry. The background, every eighth note, you hit some kind of beat or some kind of kick, but it's kind of the same thing, which really looks like music, and some kind of note which is on the, like, it's not clearly the introduction of come together as we would like it to be. But we've also run the non-negative circle decomposition with the Kullback-Leibler and the Itakura-Saito divergences, which are known to better account for the properties of audio signals. And here I will make you listen to these patterns. So it's already looks like we recognize the introduction of come together. It really looks like some kind of pattern which corresponds to the introduction of come together. So it's still not professional quality audio samples, but it kind of at least confirms that it's not done to make the hypothesis that non-negative circle decomposition extract patterns. Okay, so that's what I wanted to tell you about non-negative circle decomposition. I will pass now to Barwise compression schemes. The idea is to say other Barwise compression scheme because non-negative Tucker decomposition is already a Barwise compression scheme. The idea is to take the Barwise spectrogram and obtain a Q matrix and non-negative Tucker decomposition. But we could also run PCA, which is a standard compression algorithm, or we could use autoencoders, which are compressed models, compression models, sorry, to obtain this Q matrix. And potentially we could use more models, we just haven't tested them. And recall the time frequency bar tensor I've shown you earlier. The PCA needs to be computed on a matrix and not on a tensor. So we first have to recast this tensor into a matrix. And this is what we are making here. The idea is to take every Barwise spectrogram, take a vector out of it, so vectorize every Barwise spectrogram here. And each line of this Barwise TF is some kind of vector representing the content of on frequency and time at each bar. So here you have every line is corresponding to different bars in the song, but one line is the content of one bar in terms of both frequency and time. In tensor algebra, we call this operation unfolding. And now I have a matrix where every bar with every bar in the song and a representation, which is a time frequency representation, and we can make the PCA projection of this matrix. And then we obtain the Q matrix, and we can see if this Q matrix accounts for structural segmentation. The PCA is obtained by the singular value decomposition of the center matrix. Now, I can also use another compression scheme that we have called single song autoencoders. The idea is to take an autoencoder and to compress the different bars of a song, but we only apply it to one song. We are not trying to generalize latent space for different songs and to obtain some kind of generalization across the database. We're just using the autoencoders as a compression method. Then, starting from each bar in the song, we're optimizing the decoder with the different bars of one song. Then we just get the latent representation of each one of these bars, and we obtain a Q matrix as it was before. We compressed each bar with the encoder of the autoencoder. And again, we can use this compressed representation and compute auto-similarity matrices with this representation to finally perform segmentation results with our CBM algorithm. And what I've shown here is that PCA and autoencoders are both topping the previous non-negative Tucker decomposition. Yeah, it's kind of small, with glasses. And we obtain better segmentation results with both PCA and autoencoders. And with the 3 seconds tolerance, the autoencoder is even outperforming the previous supervised state of the art, at least to the best of my knowledge, which means the convolutional neural network. So with this unsupervised compression scheme, we managed to be maybe outperforming the strong word because its results are really close, but we are obtaining segmentation results which are really close to what we previously obtained with what other researchers previously obtained with supervised convolutional neural network. So yeah, I guess I'm happy with this result. It's already a great result to perform segmentation. So yeah, the idea is to show that different compressed representation of the bar scale could account for the structural information. And yeah, for all the techniques, the results generally fall between the unsupervised state of the art and the supervised state of the art. That is shown here. Finally, I would like to talk about what I've called Encoding MDT. It's really work in progress. It's not mature results, but it's kind of a framework which could be really interesting to. Well, I think it's an interesting idea. So basically, what we're trying to do is to take to mix non-negative Tucker decomposition with autoencoders. The core idea behind this is that non-negative Tucker decomposition is tensor optimization problem, but it can be recasted into matrix factorization problem. This is what is made here with metricization. This is what I've already called the unfolding operation. You take a tensor and you transform it into a matrix by factorizing several dimensions. So here, this is exactly what I've shown you with the Barwise TF matrix earlier. We take each of the Barwise spectrogram, we vectorize them, and we have a line. And so we have a matrix of different bars with time frequency components. But we can do this with the X tensor, as we've done with the Barwise TF matrix, but we can also do it with the J tensor. This is the exact same operation. And between both loss function, we have an equivalence. It's the exact same loss function. It's the same product. Here you have a chronicle product for the unfolding of the modes. So here in the matrix formulation, we have this Barwise TF matrix, which is unfolding of the tensor. Q is still the latent representation of the different bars. And now you have, instead of having several tensor products, you have two matrix products between the matrix J, which was matricized, which was the tensor, which was matricized and unfolded into a matrix. And you have another matrix, which is a chronicle product between W and H, and dimensions to operate. So this can be recasted in just two matrix products with respect to the matrix Q. And we want to interpret these two matrices as two fully connected layers. So now the NTD has been recasted into a problem with latent representation Q, two fully connected layers, which can create a new spectrogram X as the input. And so we can see an autoencoder with, we can create what we call an NTD autoencoder with here an encoder which can be, well, anything you want, actually, convolutions. It's a design choice. You have here the latent representation, which for each bar is a vector for each of the bar. And here the decoder is based on non-negative Tucker decomposition model. It's the matrix formulation of the non-negative Tucker decomposition. There is still a detail here, is that weights, the matrix in the non-negative Tucker decomposition, are the weights between several hidden layers. And instead of constraining these weights to be non-negative, we are applying a non-negative activation function on the output of each layer. So it's not exactly the non-negative Tucker decomposition, because the weights can be negative, but we apply the non-negativity constraints above with the non-negative activation function. And basically, you can initialize the decoder with NTD results. You can initialize with them at random. You can make choices. The idea of mixing both frameworks is to combine the performances of segmentation results of the autoencoder with the interpretability in terms of patterns of the NTD. And in an ideal world, we hope to obtain interpretable patterns in the decoder by mixing both matrices. So at least we want to obtain, and we hope to obtain some kind of interpretability in the decoder. Another advantage, or maybe expectation, to mix both frameworks is to augment, to improve the expressiveness of the non-negative Tucker decomposition model, because as I was saying, the weights are not constrained to be non-negative, but are just recasted into negative with activation functions. So the subspace of solutions with the autoencoder is actually greater and contains the one obtained with the non-negative Tucker decomposition. So it could lead to new solutions of the problem. And we can also compute new representation with the encoder design. You could easily implement constraints on the latent layer, for instance, applying a sigmoid or softmax or etc. Any activation function which lead to some kind of constrained result in the latent space, and it would be much harder to do that in the tensor framework. And finally, maybe a more practical advantage would be to use the nowadays very the toolboxes open source toolboxes for neural networks, the PyTorch TensorFlow, and to follow the recent developments in the computation in neural networks, and to, well, basically have really fast and high performance computing algorithm for the NTD. Well, or at least benefit from these advances in neural networks for tensor models. Just to show you what it looks like. So here I'm showing as I was saying, the idea is having a decoder with matrices WH and the tensor J, which are recasted into matrices, but you could still extract patterns from the decoder. So this is what I'm showing you here. I'm extracting a pattern from the decoder, and I'm going to compare the pattern obtained when I initialize the decoder at random. I'm really sorry for ears. It's a warning. And when I initialize the decoder with the NTD of this song, so it's not as clean, I would say, as the NTD I was showing you before, but you can still recognize a pattern, you can still recognize some music. And at least we have more interpretability when you initialize the decoder with NTD than with random. But the trade-off here is that when you look at segmentation results, on the left, I am showing the segmentation results of the NTD. It's a particular case I run on AWS. On the right, on the far right, I'm showing you the result with the autoencoder. So this is the Barwise compression I've shown you on the previous part. And in the middle, I'm showing you the non-negative structural decomposition autoencoder. So this framework. When here I've initialized the decoder with the NTD, and here I've initialized the decoder at random. So when I'm initializing with NTD, I'm losing in terms of segmentation results, but I'm improving the interpretability, or at least I have a better, it looks like patterns in the decoder. And conversely, I have better segmentation results when I'm just initializing the decoder at random, but I lose in interpretability. So you have a trade-off here, and it's not obvious which one should be the most important one. But of course, I was saying it's preliminary results because well, there could be many design choices to improve results, to improve the pattern, etc. Okay, I'd like to sum up what I've just said today here. So I'm taking some music in the form of audio signals, and I'm representing them into some kind of filter representation. I'm looking at this music barwise, so I'm looking back to the thing. And I've shown you 4 different paradigms of compression, so the non-negative structural decomposition, the PCA, autoencoders, and a mix between non-negative NTD and autoencoders. And this compression scheme are then, the output of these compression schemes are then used to infer structural segmentation or pattern recovery, or at least having improved interpretable output. And potentially this compressed representation could be used for other tasks. Why not? There are still kind of open problems with these techniques. Maybe the strongest one is that there is a huge need for dimensioning the dimension of compression prior to decomposition. For example, you have to dimension the latent space before encoding. And it's even clearer, it's even worse with the NTD, because you have 3 hyperparameters, which are the number of templates in either frequencies, in either rhythmic and in either Barwise templates. So here, it's not obvious how to fix these parameters and how to design these parameters to gain in segmentation or even in interpretability of patterns. One interesting future work could be using supervision to, for instance, using transfer learning in the autoencoders, or using learning some dictionaries for the non-negative structural decomposition, adding some supervision in these models to obtain better compression results. And finally, maybe a strong point just for this presentation is that these results I've shown you are only on the LWC pop dataset and should be consolidated or other genres of music on other datasets, etc. You cannot generalize outside of this dataset, so it should be made. I added the reference if you want to go through them, but now I would like to thank you for listening to me and let you the floor if you have any question. First, thank you for listening to me. That's
Yeah. It's a clarification, really.
Yeah.
At the very beginning, go back to the first few slides.
Yeah.
Okay. So when you were presenting the Q matrix, you mentioned a bit further forward. Yeah, there. So and go back to yeah. So the W is basically so W is frequency, right?
Yeah.
Okay. And H is recurrent rhythmic pattern within each bar.
Yeah.
Right. And so can you just explain again what G is actually representing?
G is G is a mix between both of these templates.
Yeah.
So if I want to have I don't know J will tell what is happening, so J adds the snare the kick, and when it's happening. It will mix the template, a column in J, which is a what, and a line in H, which is a when, and it's like combining them to say this is happening at this time.
Okay, so each potential combination of events, of frequencies in W and events in H would have a different record or different representation in G.
Yeah, it's every coefficient in G is linking two columns.
It's sort of a dictionary of combinations, in a way.
It's I'm not very clear with the term dictionary here, but it's really each coefficient in J is indicating how is mixing two templates and telling how strong these two templates are linked. So basically, if I'm maybe it's a dictionary.
No, I understand. Yeah. Okay. And then you take that and you expand it by another dimension. Is that right?
Yeah. The idea is
Okay. And then can you just explain what that process means, sort of in useful terms, so that I can understand?
Yeah. Well, for instance, here I have one drum template, but in one song you could have different drum templates, and each matrix, each J matrix is representing one different template.
Okay.
So I don't know, I can have one template for the introduction, for instance, which would be the first template. I could have one for the chorus, which will be here. One for the solo. I don't know, but the idea is to have different templates, and this Q vector here is indicated which template is important right now.
Okay.
Okay,
so sorry. So just the next thing I wanted to do is on slide 28. Can you do some dimensional reduction somewhere? Where you said you vectorize. Yeah, that was it.
Is this one?
Yeah, it's where you vectorize that.
Yeah.
So what are you losing there? You must be losing some aspect of the data when you reduce it, right?
Well, actually, here we are not reducing anything. We're just reordering the coefficients in the matrix. The visualization are misleading because actually here I have a tensor of with f times s times b coefficients, and here I have a matrix of b times f times s coefficients too.
Okay.
The idea is just that I'm taking every Barwise spectrogram, I'm making a vector, but of the same size.
Oh, I see. Okay.
Just vectorize the operation, and I'm putting it into either line in the matrix.
Oh, okay.
So it's just a reordering, and it's not up to scale.
Okay, I understand now. Okay, thank you very much.
Yeah.
I have a question regarding evaluation. What's the justification like I'm maybe familiar with the problem, so I'm not sure about what's the justification for 3-second tolerance. Like, is there any practical concern? Say 3 seconds is a good tolerance threshold for application like recommendation or
to be honest, I know that these values are standard and that, well, it's just a different level of details. I don't know right now why they have chosen. So I'm sure there is an explanation somewhere, but I don't know it, so I'm not going to invent it, sorry. But yeah, they're not at random, and probably there is. In my interpretation, 3 seconds is important because it corresponds relatively to the size of a bar. It's not exactly, it's more or less between 2 and 4 seconds in most of the examples I've computed here. Of course, you have a longer and shorter bar, but in all general, in 3 seconds can account for, are we close from a bar to the annotation, or it's kind of, I mean, this is my interpretation. I'm sure it's not the reason they designed it, but
when you split the spectrum into different parts,
yeah. On the first bit, actually. So here you have a spectrogram of the sound. Yeah, we will estimate the downbeat position, the first bit position, and yeah, we are splitting basically the spectrogram at this downbeat. So yeah, it corresponds to the first bit of the bar.
Another question about autoinference. So I remember in the slide you labeled latent representation with Q.
Yeah.
That means the latent representation is actually meaningful regarding this rich richly informative about the pattern. If I remember, that's the Q represents.
That's the idea.
So okay, that's the idea. So because autoinference is normally trained in a black box stochastic within the same way, so how do you make sure that it is the case that you capture the Q with that?
Yeah, I've used Q here to say that it's to make the analogy between different models. But indeed, in NTD, we expect the different features in Q to be interpretable. But in the autoencoders, at least in the general autoencoder, we don't, because it's local minima of the sound which correspond to non. Okay, I'm going to start the sentence. What I want to say is that in the latent space, we do not constrain Q to be non-negative. It's a latent representation, it can be negative or positive. So we do not have the hypothesis in the non-negativity that you're just adding something to obtain a spectrogram. You're just adding some musical information to obtain a spectrogram, which is actually the hypothesis between the interest of non-negativity to make interpretable error patterns, but in non-negative matrix factorization in the same way. So non-negativity allows to have only nodes, you can only add nodes, and you cannot counterbalance some kind of nonsense pattern with a non-negative counterpart of somewhere else. So yeah, in the general autoencoder framework, we do not make an assumption that Q leads to interpretable results. This is actually why we try to do some mixing between non-NTD and autoencoder at the end. Here, we make the assumption that Q is negative, and we make the assumptions of how should the spectrogram should be reconstructed from this Q matrix to follow the pattern interpretable part in negative tensor decomposition. But yeah, in general framework, we don't make any interpretable assumption.
So for the second part of the experiment, before mixing, so you just directly use the likely unpredictable segmentation as the feature for downstream task.
Yeah. It's actually the same with the PCA. Maybe here is a PCA because it's deterministic.
Right.
Yeah, we're just compressing, but PCA did not make any assumptions of interpretability in the results. We're just having a compressed representation of each bar, and we expect that this compressed representation will kind of disambiguate the overall strong similarity between feature-wise. The similarity is kind of strong. This is here. We have kind of a mostly gray approximated matrix. The idea is to reduce the similarity of bars which are not supposed to be similar, or at least having a strong contrast between similar and less similar bars. So this is the hypothesis of compression to reduce this dissimilarity, increase dissimilarity, but not to be total. I don't know if anyone has a question.
Is there any questions from online people? Okay, if that's the case,
Okay.
yeah, thanks for the talk.
Yes, thank you for inviting me and for letting me come here and present it. It was really nice. Thank you very much. I'm going to stop sharing my screen now.
Yeah.
Okay, thanks.
Yes, thank you very much.